Hello everyone, in this video we are going to implement 4-bit ripple down counter in Electric Circuit Studio, and my team members are Praveena, Preeti, Shanmugpriya and myself. Before that, we'll see few concepts behind this. Now let's see what are counters. As the name itself suggests what it does counting. So it is mainly used in counting applications, and it is implemented by using flip-flops in cascaded arrangement. And in counters, the counting depends on the number of flip-flops. If n flip-flops, then 2 power n is our count. And now we are going to implement 4 bits. So we are in required of 4 flip-flops. So our count will be 2 power 4, that is 16. So our counter counts until 16, that is from 0 to 15 will be our count. And coming to the types of the counters, it is of two types. One is synchronous and the next one is asynchronous. If you see in synchronous, there is a small difference in them both, that is in the clock input. If you see in the synchronous, all the flip-flops are driven with the same clock pulse. As you can see, only one clock pulse is used for both the flip-flops. That is, they are in synchronism. That's why it has a name called synchronous counter. And now, coming to the asynchronous counter, the first flip-flop is given with an external input, and the remaining flip-flops are given with the output of the preceding flip-flops. That's how the asynchronous counter works. And our ripple counter is our asynchronous counter. Let's see further about it. Mentioned earlier, our ripple down counter is an asynchronous counter, and the name ripple counter comes from the mode in which the clock information ripples through the counter. And this counter is designed only using flip-flops that have toggle condition. This toggle condition means it changes to other state. For example, if our flip-flop is already in a 0 state, that is low, it goes to high, and if it is high, it goes to low. This is what toggle condition means, and this toggle condition is found in a JK flip-flop and T flip-flop. And for our circuit, we are going to implement only using JK flip-flop. Here you can see this is the JK flip-flop circuit, the flip-flop diagram, and this is our corresponding truth table for our JK flip-flop. Here you can see whenever the J and K inputs are high, we obtain a toggle condition. And below is the characteristic equation of our JK flip-flop. If you implement here itself also, you can obtain Q bar as our next state. Whenever we have both the inputs high, that is J is 1 and K is 1, means K bar will become 0. So this term erases. So as a result, our output will be only Q bar. This is our output from the counter. This is the circuit for our 4-bit ripple down counter. Here you can see I have 4 flip-flops connected together in cascaded arrangement, and this JK is given with the input logic 1. Since we are implementing this circuit in the toggle condition, our J and K has to be high, so our input is logic 1. And you can notice that since it is an asynchronous counter, our first flip-flop is given with an external clock pulse, and the remaining clock pulse is given with the output of the preceding one. And when looking closer into the clock symbol, here you can notice it is bubbled with a triangle. This denotes it is negative edge triggered. So our flip-flop works with the negative edge. Okay, and next, if you are going to see the count, our count will be given in this way. Our first flip-flop will show us the LSB bit. In the last flip-flop, show us the MSB bit. This is how the circuit works. let's see with the timing pulse so that we can understand its operation. If you see on the high to low of our, this is from high state to low of our first clock pulse, our Q0 output goes from 0 to 1. This is due to the toggling action. Since this flip-flop which we are implementing are negative edge triggered, the transition from 0 to 1 does not affect the next flip-flop. So whenever our Q0 output goes from high to low, our Q1 output goes from 0 to high, that is 0 to 1 transition. This is what occurs in the next. Whenever our Q1 output goes from high state to low state, our Q2 output goes from 0 to 1. Same with the Q3. Whenever our Q2 output goes from high to low, our Q3 output goes from 0 to high. This is how our counter works, and let's now implement it in Electric Circuit Studio. And this is our Electric Circuit Studio environment. This is how it will be. For an overview, if you see, this symbol gives the delay of the circuit, and this is wire to show the path in which the circuit runs. This is run. This is next one is delete. This is rotate option. This is undo, redo, cut, copy, paste. These are the tools available in the top bar, and the three dots here gives us the menu where you can choose the new circuit or open already which you have done, save, and here this is our circuit properties and app settings, all such things. And our bottom bar contains all the components required for building our circuit. From here you can just choose the what you are in need. Here you can see we are having a flip-flops here. We are going to do our 4-bit triple down counter by using this JK flip-flop. And for drawing the wire conditions, you can use this pencil tool. Just tap the two ends from where your wire has to be drawn. This is how you have to work in this environment. Find, I have already built the 4-bit triple down counter by using 4 JK flip-flops. And here you can see our first flip-flop is given with an external clock pulse, and the remaining flip-flops are given with the output of the preceding flip-flop as a clock input, as you can notice here. And as I said earlier, our first flip-flop with an external clock pulse is going to act as an LSB, and our last flip-flop is going to act as an MSB. And when I run the circuit, our output will be shown in center of this flip-flop as high or low, and otherwise you can see the output even in the lighting of our diode. I have showed two methods from where you can see the output. And now let's run the circuit. Here it counts 111, that corresponds to the decimal value of 15, and here comes the 14, and next is our 13. It goes in descending order because it is an 4-bit triple down counter. Now it is 10. Next is our 9. 8, that is 1000. This is 7, and it goes on like this. Here you would have found that this counter has count until 16, that is 0 to 15. Since it is an 4-bit, we have got count until 16. And thank you.